All right, chemistry students, this will be the last video for chapter 7, and we ended the previous video with this slide about reaction rates. There's a separate PDF document with this and a couple other images from chapter 7 that is just 2 pages. If you printed it front and back, it would be one piece of paper. But you should really have this in front of you as we go through some of the material today. And keep in mind, like for example, what endothermic means in terms of enthalpy and that kind of thing as we go through material today. Okay, so today's goal is to look at equilibrium, which I will define on the next slide, but I want to talk about it for a minute here. And then we'll look at LeChatlier's principle. Okay, so we've seen reactions where you just have A plus B and we're forming products, say C plus D, and we have a single arrow that's pointing in the left to right direction. But if I were to write this reaction where I now sort of reverse it, C plus D producing A plus B, I could technically call this top one the forward reaction, and I could call this bottom one the reverse reaction. So we don't actually write it as 2 separate reactions like that. We change our arrow. So instead of this normal left to right arrow, we use the symbol that looks kind of like an equal sign with sort of some half arrows on it. So you need to recognize that symbol means equilibrium. Okay? And I could just write it as A plus B producing C plus D. And if I'm reading it left to right, I would call it the forward reaction. And if I'm reading it right to left, because we can go back into that direction from right to left, that would be the reverse reaction. Okay? So that's what you're thinking of for when we move on with equilibrium, is you're seeing that kind of an arrow reaction. So let's actually look. This is sort of what I just said. We've already seen reactions like that. But if we have a reaction that can move in either direction, which is many, many, many reactions, then that reaction can actually have a condition that we call equilibrium. So that is where the forward and the reverse reaction rates are equal. Okay? What that means is if all 4 substances, A, B, C, and D, are in the beaker, and they're reacting, A and B initially are really high to form C and D, and then as time goes on, the amount of C and D increases until the concentration, which is just a fancy term for the amount. There are units for that, but we haven't gone over the units in this class yet. Okay, so you think of an amount. The best concept would be maybe mole, but usually when we have concentration, we're thinking mole per an amount of substance, like within, say, half a liter of liquid or something like that. Okay? But ultimately, the amount of reactants and products remains constant. Okay? So any kind of reaction or system at equilibrium is one where you have a constant amount of reactants and products. That doesn't necessarily mean that they are equal. That doesn't mean that they're all, for example, 0.1 moles of A, 0.1 moles of B, 0.1 moles of C. But it just means that they remain constant. They're not changing. So if you were performing an experiment and measuring the amount of C over time, if the reaction was in equilibrium, and you were measuring the amount of C over a period of time, it wouldn't change. The concentration would be constant. If you were measuring B, it would be constant. Okay, so that is what equilibrium means. Let's look at an example in sort of more health, since a lot of you are going into nursing. So let's actually look at hemoglobin. Oh, I'm sorry, I forgot to minimize this. Let's look at hemoglobin. Okay. So hemoglobin binds oxygen in your red blood cells, the oxygen that we breathe, which is O2. Okay, hemoglobin in my equilibrium on the next slide is going to be abbreviated HB. Okay, so if hemoglobin is alone and without oxygen, so when you're not breathing, it's just HB alone, and when it's bound to oxygen, we can write it as HbO2. So a formula like that. That isn't really a real chemical formula because there's no element Hb. Hemoglobin is a large substance, okay? So let's look at the equilibrium system for that, okay? So I've added these two components here that I'll go over in just a second, but here's your plain empty hemoglobin without oxygen. You breathe in oxygen, and hemoglobin binds the oxygen, producing product HbO2 in this case. So we have a forward rate, that is this little k with the subscript F for forward, and we have a little k with the subscript R for reverse. So as the hemoglobin delivers the oxygen to the muscles in your body, the equilibrium shifts back to the left, and then we have empty hemoglobin until you breathe in again and breathe more oxygen, okay? So Kf, and this is just, that's a k, it's a lowercase k, is the forward rate, and Kr is the reverse rate, okay? So just to be clear, the double arrow means that this reaction can go backwards and forwards, forward direction and reverse direction, okay? So if you think about it, this is an image from a textbook that shows like in the lungs you got a lot of O2, so you're going to have this condition where we're sort of shifting in the rate going into the right direction. The forward rate is going to be really, really high, and we're going to have a lot of product. And then in the muscles, the hemoglobin's going to give away because we have low O2 in the muscles. The hemoglobin's going to kind of be like, okay, we can just release the oxygen into the muscles, and the reaction shifts to the left. So if you see below these two equilibrium expressions, we have this big gray arrow. You're going to have to be given a chemical reaction, and what you're going to do is you're going to say, under certain conditions, this reaction, this equilibrium chemical reaction will either shift to the right or shift to the left, okay? And that's what that table 7.4 has, is a whole bunch of conditions that say this type of reaction, if you raise the temperature or decrease the temperature, or if you change the pressure, that kind of thing, or if you add a catalyst, what does that do to the equilibrium? So you're going to need to know that, those patterns and that trend. So we're going to go through it, but let's actually just dwell on equilibrium a little bit longer, okay? Ultimately, you need to think like you're in the beaker. Think like, okay, I've got two substances, they're going to combine to form something in an equilibrium. Think like you're in the beaker. So if you want to, you could think of it like a graph. You could think of it like, all right, if I just have my A plus B in equilibrium with C plus D, you could actually graph amount of substance, okay? And down here, maybe you would actually just think in terms of reaction, which I'll abbreviate RxN. Well, in the beginning, you have a high amount of A and B, okay? So A and B, you could think of, they kind of go down over time if you were to graph the removal of A and B, and then, so this would be the line for A and B. And then substances C and D initially in the beaker, if you're just dumping in A and B to react, C and D, the amount are going to be low. So I'll just make this a dotted line for C and D. And so C plus D will increase, okay? So that's what I mean when I say you got to think like you're in the beaker. That should make sense until we eventually sort of reach an equilibrium state where this will level off and be constant flat, and this will level off and be constant flat. Okay, that doesn't mean they're the same amounts. It just means they're not going to change as we progress to the right in time, as we continue to measure over time. So equilibrium has another term. You need to be familiar with looking at graphs, and don't be scared of looking at the graph. Just read the axes and be like, okay, what am I trying to learn here, okay? Equilibrium is always going on. We're always having forward, reverse, okay? And maybe there's not really any change going on because A, B, C, and D are all constant, but it is a dynamic condition. So let's look at this graph. We have reaction on the X, just like the previous graph I stated. But this axis is reaction rate, which the previous video talked about reaction rate. And rate is I think sometimes you guys get scared of rate, but you're just thinking about, for rate, you're thinking kind of like the change in the amount of substance over time. So it's as simple as that. The amount you could think of in terms of moles. We will use it in terms of actually concentration, but moles over, you could say seconds. So maybe if you are an athlete and you know, like someone in track can run the 400 meter, so that's a distance. It's kind of like an amount covered, and they can run it in a certain amount of time. So they would be a really fast runner, so their rate is really fast. That's what you're thinking of for rate. We just don't have distance for these A, B, C, and D compounds and molecules. We have moles or other units of concentration, okay? So we have a red line and a blue line on here. And remember, just think A plus B, forward and reverse, forms C plus D. So the forward is going to the right and the reverse is going to the left. So the rate of the forward reaction initially is going to start high because there's a lot of A and B present that you would dump into your beaker, and then it'll slowly decrease and level out. The rate of the reverse starts out slow because we don't have much C and D to go into the left direction, so it starts out low, and then it slowly increases until the rate of the forward and the reverse are equal. So the forward rate and the reverse rate, whatever these numbers are, these K values, those are lowercase k's, they're going to be equal. So if equilibrium systems are dynamic, okay, at some point we're going to have a condition we call dynamic equilibrium, and that is basically where Kf and Kr are the same. Okay, so let me give all of that to you in some words if you were like, oh, I'm still a little lost on the graph. Okay, equilibrium systems are dynamic. We're constantly going forward, reverse, at some point. So in the beginning, the forward reaction is favored. In other words, there's more A and B present to form C and D. So reactants to product, that direction of left to right is favored. Okay. Eventually, as the reactant concentrations decrease and product is formed, in my example C plus D, then eventually we have more and more product, okay, and the forward reaction rate slows down because there's less reactant, okay. The amount or concentration of A and B reactants decreases, okay, until we eventually get, like where the two lines met on the graph, the two lines met the forward and reverse rates, dynamic equilibrium. And that's the condition where the forward rate and the reverse rate are equal. Okay, so the forward and reverse are equal. And there's not really much change going on. Okay? There's a common misconception I want to be clear about. Chemical equilibrium, look at the title on the next slide, does not mean equal. Okay, so if the forward and reverse rates, it doesn't mean that the concentration of reactants and products are equal just because the forward and reverse rates are equal. Okay, so if I have 0.1 moles of A and 0.1 moles of B, that does not mean 0.1 moles of C and 0.1 moles of D products. Okay, that's a common misconception. They can have different values, numerical amount values. It just means in equilibrium those values remain constant. So if products are maybe say 0.3 moles, it will remain 0.3 moles as long as equilibrium continues to be in existence, okay, and continues to occur. Okay, so just to be clear, two other points. Reactions may reach equilibrium only after most of the reactants have been consumed, okay? So we're going to get to equilibrium when initially the reaction favors the products, okay? Reactions that reach equilibrium only when a small percentage of the reactants is consumed. That indicates that the equilibrium favors reactants, okay? So some equilibriums will favor products and some equilibriums will favor reactants, okay? If we favor reactants, then only a little bit of the reactants are going to actually form the products, okay? So that actually occurs a lot in health. In some cases, it's more favorable to stay, for the reactants to just stay as reactants and not form products, okay? But as I said, what you're going to end up doing is looking at the conditions on table 7.4, and you're given a reaction and you're told, I do X to the reaction, or products favored or reactants favored, and you're going to need to understand why products or reactants are favored based on what you know from that table 7.4 and reaction rates, okay? So let's look at equilibrium constants a little bit more, okay? We have something called the law of mass action, okay? So chemists love numbers. We love numbers. And ultimately, when you're looking at the rate of a reaction, there are numbers of all of these substances, mole quantities of all of these substances. Essentially, all this is a ratio of products and reactants. So it's basically just a ratio. So you could think of amount. We always have product over amount of reactants, okay? Now there's a symbol for concentration that we use, so we don't have to write out the word concentration, and you're going to see that as brackets, okay? So if I was talking about concentration of substance A, I would put A in brackets, okay? So I have a new chemical reaction here, an equilibrium. I want you to stare at it closely, okay? So these little letters, the little a, little b, little m, and little n, are the coefficients that you would see in a balanced chemical reaction. And then the capital letters are all the molecules that are performing the chemistry in the reaction, okay? So that's what this says. Lowercase are coefficients, okay? And then the big letters are just the substances, okay? So what we have is an equilibrium constant. This is a big capital K. That's why I've been writing my K's lowercase. This is a capital K, and what you do to write an equilibrium constant expression is the concentration of products divided by the concentration of reactants, like I just said, the ratio. But if you notice, outside you are raising the concentration to the power of whatever that coefficient is, okay? And we're going to do a couple examples on the next slide, but you definitely need to know how to do this, okay? It'd be fair game to have a question on a quiz or an exam where you're given an equilibrium expression and asked to write, like an equilibrium reaction, and asked to write the law of mass action equilibrium constant expression, okay? Products are always on top, reactants are always on the bottom, and then you raise it to the superscript you'd have here would be the coefficients. And that's going to change because, as you already know, the coefficients can range from 1 up to, I mean, you can have coefficients of 25 or something really, really high, okay? One other note, this last bullet here, note solids and pure liquids don't appear in this equilibrium constant expression. So if you had an H2O pure liquid, he would not appear at all on there, okay? Because concentration usually deals with something in the aqueous or liquid. In a liquid, it's aqueous. We do not also include solids. So if you had like calcium that was a solid and you mixed it with water and then you formed some aqueous substance, this would also not appear. So this doesn't appear and this doesn't appear in the law of mass action, and that could be a common mistake that students put in. Okay, so let me show you two, and it's because these don't change. These don't change. They're not going to change concentration in equilibrium, so they don't need to be part of this expression. All right, let me show you two examples. Okay, so this would be a perfectly good quiz question or even homework question. All right, so you're going to express K, the equilibrium constant K, big capital K, for the given expressions. Okay, so I have 3 gas substances. 2 of them are products, and don't forget we have a coefficient of 2 here. Okay, so it doesn't matter which product you write first, but we have both products. Okay. And since CO has a coefficient of 1, I'm not going to write anything next to it, but H2 has a 2 here, and so it would have a superscript 2. And then you write the reactants. Put it in brackets. CH3OH, okay. Coefficient of 1, so we don't actually write the 1. And that is it. That's the expression. Okay, so I'm going to actually erase that and give it to you how I've typed it out. All right, that would be the equilibrium expression K for the A reaction you're provided at the top. The bottom reaction, you need to be clear. We've got aqueous products with coefficients of 1. So your numerator, the top part, should be pretty easy. The bottom part is not going to include the water because that's a pure liquid and it doesn't get included. And then the bottom, the denominator, is going to have the NH3, and there are no superscripts in this equilibrium expression because all the coefficients are 1. Okay? Okay. We'll get into it more, but K is basically giving you a statement about whether the forward or reverse reaction is favored. Okay? So it doesn't matter the speed of the reaction, the rate, it just is whether the direction from left to right is favored or from right to left is favored. Which one is favored? That's what you're thinking of. That's where we're going. Because there's going to be, you can calculate, there's going to be a number for this. What you're going to need to do is recognize based on the number, oh, that favors products or that favors reactants. In other words, shifts. If it favors products, then shifting from left to right is favored. Okay, if it favors reactions, the reaction will go from right to left if reactants are favored. Okay, so let's look at some numbers. This is what I just said on the end of the previous slide. If you have a really big K value, equilibrium favors products. And that should make sense because if it's concentration of products over reactants raised to whatever the powers are of the coefficients, okay, if the numerator is really, really big, products are favored. If the numerator is big, K is going to be a very large number. If the denominator is really big, then K is going to be a small number, which is why this is less, less, less 1. So small k, then the equilibrium favors the reactants, okay? So you should practice writing, but you should practice writing the products over the reactants, okay? And I'm going to go ahead and give you the numbers here for, you don't have the actual values of these concentrations, but if I told you here's the equilibrium expression, there's the law of mass action, the equilibrium with the substances all written out, and this is the actual value. Okay, so we'll get to what is big enough to favor products and what is small enough to favor reactants, but that's a pretty large number, 10 to the 19th. Remember, Avogadro's number is 10 to the 23rd, okay? So you should automatically see a large K here means products are favored. So that expression favors products. This entire reaction, whether you know what the chemistry is of that or not, based on this big number, you should know that products are favored. Okay, so then the next one, if I gave you the value here, I have a very large negative superscript, which means this is like point a whole lot of zeros for a long time and then 1, which is a very small number, and therefore the reactants are favored in this expression. Okay, the reactants are favored. So your book has actually a really good image of K. So this bottom image, you've already seen this top part, and just this top part will help you recognize, remember, products over reactants, okay? But this bottom image is like, so how big? How big does K need to be? If I just say K is greater than 1, favors the products, what exactly are you, how big, okay? Generally, if we've got our 1 here, more products than reactants are present. Okay, so K very large as you go basically from 1 to that direction. This is the number 1. Then the products are favored. If we go less than that, the reactants are favored. And if we get really, really small, the reaction is hardly going from, you know, if you have A plus B to we can even use the M plus N. If you have a really, really small K, then it's hardly going at all because A and B are favored, and we're just going to sit out as A and B in the beaker. Okay? Okay. The only other thing I want to mention for those of you that don't like writing units is K doesn't have a unit because these superscripts can get really large. These little lowercase superscripts here, they can get large, and so chemists just decided that K does not have a unit. It will not have a unit because it could vary so much. Okay. So let's now go into LeChatlier's principle. What this means is if I have an equilibrium sitting in a beaker, I can alter the equilibrium. I can say, oh, it's favoring products. I'm going to do something to push it back to the reactant. So it's kind of like if someone were standing up and you were to push them over and push, the harder you push, eventually they're going to not be able to stand on their 2 feet. They're going to have to move a foot so they don't fall over. And they shifted their body position in order to not fall over, to be able to continue to stand up. That is what LeChatlier's principle is doing. We are adding a disturbance to the equilibrium, and that system, that chemical reaction, is going to shift to go back to equilibrium. Okay? And what can we do to change? Sometimes temperature will affect equilibrium, concentration. Like I said, we haven't gone over this unit yet, but for now you can think of it in terms of amount of moles. Okay? Pressure or volume, especially with gases, because if you think you have a container and its gases filled the volume and shape of their container, what if I squished that container down? Okay, it's the same amount, but now I've squished it down. What does that do to whatever the equilibrium expression is? Or we could add a catalyst. Okay, so all of these are listed in that table 7.4, and that is where you start to see, okay, in a certain type of reaction, like endothermic or exothermic reactions, temperature can really affect them because temperature is very involved in endothermic and exothermic reactions. Okay, so let's look at an example. If you remove ice from a freezer, it will automatically melt to minimize disturbance. Okay, that solid ice cube is not going to remain frozen on, say, your kitchen counter. Okay, it will melt. It will change from solid to liquid. So you could think of it like an equilibrium of just the phases. Okay, that's what you're sort of thinking of. You add some pressure, heat from the kitchen, surrounding kitchen air, and that pressure changes the ice. It changes from solid ice to liquid. Okay, so let's actually look at 2 reactions here at the bottom. Okay, it's the same reaction, but what we're doing on the left is adding heat, and on the right we're removing heat. So that is the disturbance that we're adding. So we have N2 plus H2 yields ammonia. Okay, so it's a balanced reaction. And just to be clear, because heat is written as a product, you should already automatically from earlier in chapter 7 know that this is an exothermic reaction. Okay, it's an exothermic reaction. And this is where you think of heat as a product. Okay, so if I'm adding heat, if I'm raising the temperature of this beaker, what is that going to do to this reaction? Well, if you see, I'm adding, it's kind of like I'm dumping product into this reaction, and if you see the gray arrow, the whole reaction is shifting to the left. Okay, if you notice, that actually also will lower the K value, because if I am decreasing the amount of products, K will get smaller until we go back to equilibrium. Okay, if I remove heat, no matter how I remove heat, maybe I cool the beaker, doesn't matter how I'm removing the heat, it's like I'm removing product. It's like this is getting removed out of the beaker, and that'll shift the entire equilibrium to the right to try to rebalance back to equilibrium. Okay, so let me give you some words for that. All right, any change that affects the equilibrium, any kind of thing you add to it, LeChatlier's principle says that system is going to counteract that change. Okay, Systems want to be at equilibrium, and they're going to work to get back there. Okay, so LeChatlier's principle is actually if a system at equilibrium is disturbed, the system tends to shift its equilibrium to counter the effect of the disturbance. So that's the actual legit textbook definition. But that's kind of like if I push hard enough and you're standing on 2 feet, instead of falling over, you're just going to maybe widen your stance so you don't fall over, okay, and that you can remain standing. Okay? So let's look at another couple examples here. Given this reaction at the top, okay, I'm going to give you a condition. Add CO into the container. So the first thing you know is that CO is a reactant. So I'm dumping in more reactant. Well, if you increase the amount of reactants, automatically you should be like, okay, well then we're going to have to shift to form more product so that we get back into that nice dynamic equilibrium. And if you see, this image from your book actually shows this arrow is a little fatter and bolder than the lower arrow, because this is kind of trying to represent we've shifted to the right so that we can get back to equilibrium. Okay, this lower image is actually showing it as dot, 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 dot. So if this increases, the carbon monoxide, then this decreases, okay? And this increases. In other words, I dump in more reactant here, the CO will react with H2 to form the product, okay? So H2 decreases, and therefore product increases. But to overcome the whole, to overcome the disturbance, the equilibrium will remain constant once we have finished our shift to the right, okay? Because it is equilibrium. Sometimes you see it written K with a little EQ underneath it. Okay, so you have to think like you're in the beaker. I'm going to go through several examples using one reaction. Okay, I'm going to go through several examples on the next slide. Okay, so one reaction, 1, 2, 3 components. So it's like A plus B forms C. All right, I'm even giving you here the enthalpy of this reaction. Knowing that I have a negative symbol here, I know it's an exothermic reaction, so you're thinking of heat as a product. Okay, so I have 8 disturbances listed here, 8 different disturbances. Okay, and if you notice, they're all gases. They're all gases, so you need to look at what pressure does to gases on that table 7.4. Okay. So if I dump in more O2 while I'm adding reactant, you should know, all right, what is favored? So that's what I'm going to show when I go through all the answers here. What is actually favored? I want to know, is product favored, reactant favored, or is there basically no effect based on whatever disturbance I've added? Well, hopefully you should know if I'm dumping in more reactant, the whole thing's going to shift to the right, and the right is the product, so product is favored. If I'm removing, so somehow I figured out a way to get rid of this guy. So he's leaving. SO3 is leaving. Okay, that's what number 2 is saying. Removing SO3. Well, if he's leaving, the equilibrium is also going to shift to replace him, and it's still going to shift to the right and form more product, because SO3 is leaving, we got to replace him. Okay. Now, if you're compressing the gases, this is where you were thinking like a box that big, and now I have a box this big. Okay? This is where you need to go back to entropy and moles of the system. I have 2 substances on the reactant side, 2 substances. So if I'm sort of like cramming the space smaller, this reactant side has higher disorder, higher entropy, higher S. The entropy is S symbol, remember? So we are actually going to shift, when we squish our size in gases, we are going to shift to whichever side has the fewer moles of substance, the fewer amount. Okay, well I have 2 moles of one reactant and 1 mole of O2. So 3 moles are on the left side and only 2 are on the right. Or you could just look at it in terms of 2 substances on the reactant side, 1 substance on the product side. So if I have to shift to overcome the compressing, the decreasing box, I'm going to shift to the side with fewer moles, which is the product side. in this case. As a side note, if that is the squish, so what we just did was like this, we're sort of squishing into a smaller box. Then if I, going down to number 5, double the volume of the container, we're going to think the exact opposite. So you should already know the answer to number 5 based on our answer to number 3. But let's go to number 4. So if I cool, so this is lowering the temperature. This is where you have to go back and say, okay, what does lowering the temperature do to an exothermic reaction? We'll think of heat as a product, so you could have plus heat over here. Well, if I lower the temperature, what is that going to actually favor? It's going to favor product because we're going to end up adding, the system wants to go back to adding heat, to producing that exothermic heat in an exothermic reaction. Okay, so 3, if decreasing volume favored the side with fewer moles, then hopefully you should know that increasing the volume of the container, when all these guys are gases, is going to favor the side with more moles, which is the reactant side. Okay? And if 4 was decreasing temperature, 6 is increasing temperature. So think of it like I'm dumping heat in here. It's like I'm adding product. That will favor a shift to the left or the reactant side. And number 7, all right, adding an inert gas helium to the container. So he's not even part of the chemical reaction, and he's not going to react with anybody in there. That has no effect. Not going to do anything. Adding a catalyst. I would have to tell you somehow in the provided reaction that the oxygen acts as a catalyst or something like that. I would have to tell you that this reaction takes place with a certain catalyst or something of that nature in order for you to actually be able to say whether a catalyst has an effect. And since that's not provided, there is no effect for adding the catalyst. Okay? So that is the end of chapter 7, but I did want to give you a quick summary. This image goes actually all the way back to ionic bonds from chapter 3, covalent bonds from chapter 4. You learned about all kinds of chemical reactions in chapters 5 and 6. And this all in green is all chapter 7. So we had a video on enthalpy alone, and then we looked at entropy and delta G and whether a reaction is spontaneous or not, as well as rates of reactions with the reaction coordinates that look like this with energy of activation. And today it was all about equilibrium and LeChatlier's principle. Okay, so this is a really good sort of review image if you want to go over this. Okay, so thank you for listening.